The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Piek is an associate and specialist in tunnels and underground construction at Arup. He heads the tunnels team in San Francisco, working on a number of metro roadway and water projects on the West Coast and South America. His most recent projects include LAX Crenshaw Corridor, the San Francisco Central Subway, Anillo Vial Periférico in Lima, and a lead tunnel engineer for the boring company. So,
thank you, everybody. Today I'll be talking about cementitious and non-cementitious grouting for underground construction. It's a little bit out of the normal round for an ACI conference, but I hope you guys find it interesting. This is the Crenshaw LAX transport corridor. It's located right here in Los Angeles, and is the first of several metro projects that are now under construction. This project is an extension from the existing Expo line and travels kind of south and connects up to the Green Line near the airport. The contract value is about $1.4 billion, and the contractor is a joint venture of Walsh-Shea. We are the designer with HNTB. The NTP was in September of 2013. We went pretty much straight into design, and construction is ongoing, looking to open in 2019. Flipping it on its side a little bit and a bit more of an explanation of the project. The first part over here on the right-hand side is fully underground. Consists of 3 stations and about 1.6 miles of tunnels. And then it goes into a series of cut and cover structures, elevated at grade structure, and then back into a cut and cover section near the LAX airport before it comes up on the Green Line back over here and connects up to make a nice loop system. Everybody will finally be able to get almost to the airport using the metro until the people mover that's scheduled to go into construction will link it all together. Soil conditions on the site are mainly alluvial soils in varying age, between young alluvial materials to older, partially cemented alluvial materials. And one of the reasons I mentioned that is because in the geotechnical baseline report, there were varying levels of cementation of the soils that were present. In some locations, up to 20% of the soils were cemented. In hindsight, that probably should have tipped us off to something that was going on here to pay closer attention to. When doing cementitious or non-cementitious grouting, you should always pay attention first and foremost to what the Sieve analysis showed. And usually what you're looking for in here is to figure out at what percentage of fines fall below the 20% level, because that's going to tell you whether or not what techniques you need to use in order to go ahead and treat the ground so you can actually do civil work construction. In general, what you're always looking for is there's 3 major types of cementitious grouting, and then before it goes to like a chemical grout. If your fines are around just under a bit of a millimeter, you're looking at using a normal grout to go ahead and treat the ground. Below that, you got fine cement grouts, could be your microfines or your ultrafines. And then beyond that, you're looking into doing sodium silicate mixtures just under a pressure grouting situation. The first and the largest station in the works is the Expo line, the Expo station. It's about total length of about 1,000 feet and is the terminal station for Crenshaw. One of the things that was noticed is that there were actually 2 different aquifers, and in order to go ahead and build the station to begin with, one of the worries was that you were going to get basal heave due to this water pressure as you start to excavate down. And the selected construction method here was to use bottom-up slurry walls, and then grouting the open windows between those panels due to the number of large sewers and other utilities that were in the way, and we couldn't obviously create a continuous panel wall all the way around it. So what we did was we were looking at using jet grout between those open windows to close those up and be able to excavate down. It initially required that we do jet grouting across a large majority of the base of this thing, and had about 30,000 cubic yards of jet grouting. And when you're looking at about $500 a cubic yard in place in jet grouting, that's a lot of money. So instead of going ahead and looking at that, what we did was we decided to actually invest in making the slurry walls deeper, going ahead and embedding them into a clay layer that was deeper, and then using relief wells to essentially eliminate the ground treatment. So in certain cases, just getting a little bit smarter about how you're going to schedule out your construction ended up saving us quite a lot of schedule and money. The principle of jet grouting, for those that aren't familiar, is that you're using a large lance and a mixture of fluids to go ahead and treat your ground. Most commonly, we use a 3-portion mix of air to kind of pre-cut the ground, associated with water, and then you're injecting your cement slurry mixture. And you're usually going ahead and putting in primary columns, and then you're coming back and doing secondary or tertiary columns to go ahead and close everything up and make them all watertight, or at least as watertight as you can get it as you go down. This is some of the results of what you can get in favorable conditions with jet grouting. Very large, essentially like stone columns in place. And some of the things that happened early on in the project as we got our test results back, when you're doing jet grouting, you're taking wet samples, which is basically you're injecting material into the ground. And so spoils are rising up to the surface, and you're basically sampling them, and you're going ahead and using your standard concrete sampling on that. We started getting back strengths that were pretty high from our wet samples, and then you do coring as well, in situ coring, and we got some that were as high as 6,900 psi. Now, that's really high for jet grout, and it started to look at creating, while this was great for some of our stuff, it also can be difficult in other things, especially when you have to excavate through it. So one of the things that we have to do is launch a tunnel boring machine out, and usually we do ground treatment in front of the station walls, so that as we break out into the ground, we don't have influshes of soil and material. Well, you can imagine that mining through 6,500 psi ground is going to create a lot of wear right out the gate on your tool that you're using to go ahead and excavate out this long subway system. So we had to have a different solution adopted based on what our site conditions were giving us. And we looked at it, and our preferred treatment was going to go ahead and move away from using a cementitious grout and instead using a chemical grout, where chemical grouts usually don't give nearly the strength, but would give you enough strength to actually do what you're looking at getting accomplished. So we looked at microfines, ultrafines, and then we eventually went with a straight sodium silicate solution to go ahead and do this. One of the complications was that we had a roadway in front of our station box, and at Rodeo Road and Crenshaw, it's a fairly busy road, and shutting down that street to do ground surface treatment was not the preferred option. So we looked at a couple different things there. Just a principle of chemical grouting. Our silicate-based grouts are sodium silicate with a reagent and then water. So really it flows like water and has that same viscosity. And again, the strength that you get is directly related to how much you can put into the ground and how porous the ground is. So if you have a lot of fines and you can't pump it in, you're not going to get nearly as much strength as if you were, say, grouting like a clean sand. So unlike jet grouting, where you're basically pushing a lance into the ground and then slowly withdrawing it as you're injecting, in chemical grouting, you actually pre-drill, install what we call a sleeved port pipe, and then you come back in with a double packer and you inject into the ground so that you can actually do it in stages in particular locations. So in this case, this was Central Subway, where we did a series of groutings underneath buildings and underneath BART to actually go ahead and identify and basically this is a little cartoon of, you know, kind of lances that get formed, but it's very much this way in the ground as you're injecting it. And the idea, again, is to use a primary, secondary, tertiary approach in order to go ahead and get the coverage that you need. And then also the sleeved ports allow you to come back and do re-injections if you need to go ahead and get the coverage you want. The breakout, we looked at two different options. One was the grouting from inside the station walls here. This is kind of shown in elevation. And this would be the area that we were treating for the machine to break out. And then the other one was from within the street, which is a plan view up here, kind of with these hexagonals showing the size of the areas that we were hoping to treat, which each pipe basically drilled vertically from the street down in there. And when it came to cost, this was the best one. So we asked Metro, pretty please, can we go do this? It's going to save schedule and money, and they agreed to it. So we had a series of shutdowns in order to get that done. The machine itself and some of the other concrete works that we were involved with, we designed out the precast concrete segmental tunnel lining, which is a traditionally reinforced segmental lining. We also designed out the cross-passage temporary and permanent works, track bed and the walkway inside. The tunnel station seismic joints were quite interesting because of the different behaviors between the station and the tunnel in a seismic event. And then we had to do all that ground treatment at the tunnel station interfaces and the cross passages. So cross passages are oftentimes used for evacuation in between tunnels, but oftentimes become equipment rooms for the operations and maintenance people. We combine the two uses into one, but because these are short sections, these are usually hand mined. So you have to do ground treatment in order to go ahead and make sure that you know, the ground doesn't come in on you and move. This is an active roadway above where we were working, so any you know, cave-ins here would obviously directly start affecting the roadway. What happened in the course of the project was we mobilized out our contractor to do jet grouting at Expo Station. And as we were getting the test results back at Expo Station, we were getting those extremely high break strengths. And we started getting worried, well, we're going to have to mine through, you know, 6,000 PSI concrete. And we looked at trying to switch and go to chemical grouting. But unfortunately, at the locations where we had the cross passages, we had too many fines. And so the possibility that actually we would mine into an untreated section of ground outweighed the benefits of trying to go ahead and do something different. So we ended up having to essentially, for schedule reasons as well as for risk reasons, stick with the jet grouting, which we tried to go ahead and eliminate some of the problems by going to 8-foot columns and using a wider spacing in order to go ahead and maybe get away from those high break strengths that we were getting. Unfortunately, the test scores came back like baseball bats. I mean, they were just like fully big pieces of concrete. And we had very strong cement-like results, even higher break strengths. One of the things that you can do as well is you can always do a back analysis of your statistical results to get your design strength. It came back as higher than 2,000 PSI for design. So we were essentially going to be mining through a big block of concrete. And that ended up going ahead and being used as a benefit at the same time by going ahead and eliminating a lot of the internal support that we would have had to have in the mainline tunnels and a lot of the cross-passage internal support. So this is some of the results of versus depth here. Break strengths on the vertical axis versus depth on the horizontal axis. You can see some of these as high as 7,000 and the low on the low end right around 1,700. So pretty tough stuff. And just show you a little bit. So this is a road header trying to excavate through our treated soil. And as you can see, the stuff is just very, very tough, difficult to mine through. Took a long time, and this is kind of one of the lessons learned about this whole job. I mean, overall, we ended up making it work, but in hindsight, when you're working in the LA area, unless you want something like this to happen on your job, just keep this in mind. Some pictures of the Crosspassages as they were being mined out. It made it very stable. There was no groundwater at all. From a standpoint of sleeping at night, you knew it wasn't going to come down on your head. And in the end, we ended up eliminating all the shotcrete on the inside. We only had a picture frame around the outside of the tunnels. And we just put up a little bit of shotcrete to go ahead and make a nice smoothing layer to put our membrane up against our waterproofing membrane. And yeah, I just want to show you some pictures of the concrete works since this is a concrete seminar. This is the walkway inside the finished tunnel with the invert already cast. This is the tunnel station seismic joint. With all this white is an HDPE. We need to use actually something stronger than PVC for metro projects because of the methane in the ground in Los Angeles. And this is some of the station concrete works starting from the invert and casting up the walls. Some of the moving formwork that was gone, and then some of the Crosspassages. The Crosspassages are being cast as we speak, and we'll be done with pretty much all the concrete work before the end of the year, and then start all the rest of the fit out. So it's always good to take a big step back on these projects and kind of think about what you did right and what you did wrong. One of the things is that Metro does like to go ahead and release a lot of their contracts as design build, to go ahead and allow the contractor to kind of adapt their means and methods to what they want out of their specifications. And that's great, but we also need to be able to adjust them in the field and have that flexibility as we go through to make sure that if we encounter something in the field that's different than what we expect, that we have the right systems in place to go ahead and make those changes occur in a timely fashion so that we don't have engineering decisions being made based solely on schedule. So that's one lesson learned. The other one is, as engineers, we do need to challenge ourselves and critically evaluate what we're putting out. There were several times we went back and forth between the possibility of simply just mining out the Crosspassages without any ground treatment. And that carried a level of risk, but was that level of risk commensurate with schedule delay and the complexity associated with what we knew the results of the jet grouting was going to be in the Crosspassages. And as owners, we also need to understand that while we set our contract documents to be as good as we can, they're not perfect and may not always have the best intentions for the project as we go ahead and we get into the works. But I appreciate your attention, and thank you very much.